Hello and welcome to the fifth and final video of the FP2 chapter Further Argand Diagrams. Quick review for a GCSE idea on the screen here, which will lead into our ideas in this video. Given f of x in the diagram, here it is, a cubic graph. Sketch these three graphs here, so we're transforming. F of x minus 1 shifts this graph 1 unit to the right, which looks something like this. 2 times f of x is a vertical stretch 2 times bigger. So that stretches it up here somewhere. Goes through the same points on the x-axis. And finally, half x inside the bracket here is a horizontal stretch, and intuitively it looks like it should be a half times stretch, but actually it's a 2 times stretch because you divide by this number, whereas you multiply by this one. So that will go sort of over here somewhere, come down through 0, over here, and up through 2. This leads into what we're doing in this video because we are transforming loci from one complex plane to another complex plane. To see how this works and to see the link with what we just did there, let's look at this. We know 4f of x is a vertical stretch of f of x with a scale factor of 4. Now let's have something written slightly differently and see what happens. What is the effect of the transformation m equals x over 2 on the function y equals x squared? This is saying we're going to make the x coordinate into an m coordinate. So instead of an x-axis, we'll have an m-axis when we sketch this. And the relationship is m equals half of x. Now, of course, the very first thing we're going to do in order to apply this is rearrange it so we know what x is equal to in terms of m, so we can substitute it in here. X is equal to 2m, so x squared is equal to 4m squared. And that's what we have here, 4m squared, with the m-axis here instead of the x-axis. And you can see that the relationship between this graph and this graph is that this is a vertical stretch with a scale factor 4, just as we had here. So this is another way of writing this same thing. So this sort of idea is going to help us understand transformations in the complex plane, because we're going to go from an xy plane, the z plane, into a uv plane, which is going to be called the w plane. And we're going to use the transformation t, where t is going to be given as an equation, w is equal to some function of z. So this is telling you how the w complex number relates to the z complex number so that we can transform from one plane to the other. We'll start with some simple examples just to see how this works, because you need to be able to determine what a locus in one plane becomes in the other plane. We do have a standard method for this, but in the second half of the video we'll see some more involved examples where we need to adapt the method and it becomes a little bit more complicated. But to begin with, it's quite simple. You rearrange your transformation to make z the subject. So we've got w equals 3z. We need to know what is z in terms of w over 3. The reason we do that is so that we can substitute this into the locus we know in the z plane. Modulus of z is equal to 2 will become a modulus of w over 3 is equal to 2. Now, in one sense, that's the transformation finished, but in order to interpret what this locus is, we should rearrange it into something familiar. We've got the modulus of w over 3, and we know that can be split into the modulus of w divided by the modulus of 3, and the modulus of 3 is just 3, so this becomes the modulus of w is equal to 6. Which is a very similar expression to this. It's a circle with the center 0, 0 and a radius of 6. So it has become bigger. It's an enlargement, scale factor 3. And that may not be a surprise to you, given this statement here. Looking at another example, w is equal to z plus 2 plus I. Same approach, rearranged to make z the subject, gives us z equals w minus 2 minus I. Substitute that into the known locus. This becomes this, rearrange to interpret the new locus. Well, we don't need to rearrange much here. Let me just make it a little bit clearer that this number here is 2 plus I, and that is acting as our W1 in place of our Z1, and that tells us the center of the circle has shifted from 0 to 2 plus I. So it's at 2, 1 with a radius of 2. So the radius hasn't changed, it has just moved or translated over here. And again, given this statement, that's probably not a surprise. Third and final simple example is this. This is slightly more interesting because you might not be able to see what's going to happen just by looking at this. Rearrange to make z the subject. Z is equal to W divided by I. I don't really want I in the denominator though, so I'm going to multiply top and bottom by I, which gives me a -1 on the bottom and an I on the top, so this becomes minus WI. That's a little bit neater. Substitute it into the known locus. So here we've got the argument of z plus 2 equals pi by 4, and this becomes the argument of minus WI plus 2 equals pi by 4. Now the third step here, interpreting this, is going to take a little bit more work, because we need this in a more familiar format. And what we usually want is a z plus or minus something. So the z is usually by itself without anything else. That's what I want for w. I don't want this minus I here. So I'm going to force out a minus I by factorizing it. So we're going to force it into minus I, and that will give me w here plus 2I. And I know it's plus 2I there just by considering what would happen if I expand this out. This would become a minus 2I squared, and the I squared would be another minus, so that would become a plus 2, which is what we had. But why do that? How does that help? That helps because here we've now got the argument of one complex number minus I times another complex number, w plus 2I, and we know the argument of two complex numbers multiplied can be rewritten as the argument of the first one plus the argument of the second one. And that's really helpful because now we do have something in our more usual format. This is the argument of w plus 2I, so minus 2I is the point at which this half line comes out of, but we need to deal with this. That's not so bad because the argument of minus I, we actually know what that is. Minus I starting from here, minus I is down here. And the argument of that, going clockwise, is minus pi by 2. So I can just change that into the thing we know it is. And then bring this on to the right hand side. Pi by 4 plus pi by 2 is 3 pi by 4, and that gives us our final locus. The argument of w plus 2I is equal to 3 pi by 4. So that's down here somewhere on the v-axis, and it's coming out at an angle of 3 pi by 4, so it looks like this. And you might be able to see what has happened here. This is a rotation from here to here, about the point 0, 0, 90 degrees or pi by 2 radians anti-clockwise. And that gives you three standard results. We've had an enlargement, scale factor k, with kz where k was a real number. We've had a translation of AB, where AB is the z1 complex number here. And we've had a rotation anti-clockwise of pi by 2 radians, center 0, 0, with IZ. And while it might be useful to recognize these, you will need to be able to apply this method to more complicated transformations, which is what we're going to go into now. Using the same method, show that the transformation, this, maps this locus in the z-plane onto this locus in the w-plane. And you can see straight away this is a much more complicated transformation because in the z-plane this is a circle, and in the w-plane it has become a line, a perpendicular bisector. Changing a circle into a line is not something that is easy to do with our GCSE transformation processes, but here it's a fairly simple equation. So I'm going to follow the same process up here. rearrange this transformation to make z the subject. We've got wz is equal to z minus 1, so 1 is equal to z1 minus w, z is equal to 1 over 1 minus w. Now we substitute this statement into the locus that we've been given in the question. Z minus 1 is equal to 1 becomes 1 minus 1 over w minus 1 equals 1. Now I have to rearrange to interpret the new locus. Specifically, I need to finish with this statement here. To do that, I think the first thing I should do is combine these into a single fraction. So that will be 1 over 1 minus w minus 1 minus w over 1 minus w is equal to 1. And then we can see that the 1 minus 1 will disappear and the minus minus w becomes w over 1 minus w equals 1. Now I can split my modulus and bring the denominator onto the other side. Multiply by 1 is just 1 minus w. Now that doesn't look quite like this, but because of the modulus symbol, I can factorize a minus 1 out of this to switch the places, and the modulus of minus 1 is just 1. So because of the modulus, I can just directly swap those round. And we've shown that this is true. Now there's a second part to this question that says the region this, so we've got our circle here, and now it's saying inside the circle in the z-plane is mapped onto the region t in the w-plane. Shade the region t on an Argand diagram. So first of all, I need to know which region is it. To do that, I change my equal sign here, which I have here, into a less than or equal sign. So this is actually a less than or equals, and I'm going to follow through the working, being careful that if I ever multiply or divide by a minus number to flip that symbol the other way. So here it's fine, here is fine, here is fine. Be careful here, but although I have multiplied by something, this modulus is definitely going to be a positive number. It must be, so I don't need to change the sign. So we've got this, which we know how to interpret. If I sketch this on an Argand diagram, remember we're now in the w plane, so this is not x and y, but u and v. So it's here, and let's say here. The perpendicular bisector must be a vertical line going through half, and the side that is closer to the 0 point is this half here. So this region is t. So once you've substituted in to the locus, most of the work is interpreting or rearrange in order to interpret what you've got. We're going to take that a little bit further now and say what happens if this locus is not quite so easy to interpret once you get to the end of this process. So here's an example of this. The transformation t from the z-plane to the w-plane is given by this formula. Show that the image under t of the circle with equation this in the z-plane is a circle C in the w-plane. State the center and radius of C. Okay, first of all, notice that we haven't been given a locus in a locus form, but we do have an equation of a circle, and from this I can make the locus in the z-plane. This is the same as saying the modulus of z is equal to 2, because we've got a center of 0, 0, and a radius of square root 4, which is giving us the same locus. You might not be given the locus explicitly, you might have to figure it out from the information in the question. Now we go through our process, rearrange the transformation we've been given to make z the subject. So we've got w, z plus 1 equals 3z minus 2, wz plus w. I'm going to bring the 2 on this side, factorize the z on this side, to give this. Now we substitute this into the locus that we decided upon. So this becomes this. And as before, we can split our modulus to make it this, and then bring the denominator on the other side. And then if I want to, which I will do just to make it look more familiar, I can switch these around because of that modulus symbol. That's the same thing. Now effectively we've finished. This is a locus and we recognize what it is, and we know what it is, it's a circle, but this is one of those circles where we don't know where it is or what the radius is. And it involves a lot more algebra. Usually we would now substitute x plus yi for z, collect real and imaginary parts, get rid of the modulus symbols, rearrange to get a circle equation. And unfortunately, that's what we've got to do. We've got to do all of that process, even though we've done all of this work so far. But be careful, do not use the letters x and y for this w complex number. X and y relate to z, and we've already used them here. When you do this for w, it's all exactly the same, but just use, instead of x and y, u and v. But it is the same process. So we've got u plus vi, u plus vi, collect real and imaginary parts, then get rid of the modulus by doing the real part squared plus the imaginary part squared, square rooted. Then square everything, not forgetting that this 2 squares to a 4, and at the same time I'll expand out those brackets. Now we need to expand this bracket, rearrange things, and get a circle equation involving u and v. It does not look like the numbers are going to be very nice, but we'll follow through. Now divide everything by 3 and complete the square as usual. And although we've got some fractions in here, this doesn't end up too bad. We've got 14 over 3 here, and these numbers collect on the right to give 100 over 9. So our center point is 14 over 3, 0, and our radius is 10 over 3. And there we go. So there were 2 extra things here to realize. First of all, be careful, you might not be given the locus explicitly in the question, and you might have to use w equals u plus vi to interpret the locus, just like we did z equals x plus yi in previous videos. Okay, there's plenty to practice there, although we haven't finished yet. You could stop now and do some of the questions from exercise 4e and the chapter 4 review exercise, but the final part of the video will go into some harder examples and a slightly different method of dealing with them. So the difference here is that not all questions will give a clear locus to transform. Now the previous example, we already had that situation where we had to find the locus ourselves from the information given in the question. But what I mean here is that you might not have enough information to make a locus, in which case we have to approach it slightly differently, but we can still do it. We can substitute w equals u plus vi not into the locus we found, like we did in the previous example, but into the transformation itself. Only do this if you don't have a locus to substitute it into. The alternative method then is to start the same way, rearrange to make z the subject, then substitute w equals u plus vi directly into the transformation, Then often you have to collect real and imaginary parts to use information given in the question about x and y and their relationship together to form an equation, because the real part will act as your x, the imaginary part will act as your y, and if you've got a relationship between these two, you can make a relationship between these two which will involve u and v. That equation then can be simplified to give you your locus in the w plane. These questions tend to be a little bit harder, so let's have a go at one of these. A transformation t of the z-plane into the w-plane is given by this. Show that as z lies on the real axis in the z-plane, then w lies on the line L in the w-plane. Sketch L on an Argand diagram. So as you see, we don't have a locus. All it says is z lies on the real axis. What we can get out of that is not a locus involving z, so much as a simple statement about x and y. If z lies on the real axis, that is the same as saying y equals 0. But you can see, rearranging this to get z equals something in terms of w doesn't help us substitute in this directly, but we do need to start with that. So let's go ahead and rearrange. Okay, this is where we would normally substitute this into a locus, but we don't have a locus involving z, and we don't even have enough information like we did in the previous example to create one. All we've been able to create is this statement here. But we know that z is x plus yi. So if we can rearrange this into real and imaginary parts, then we can equate the imaginary part here with the imaginary part here and say that bit must equal 0 because y must equal 0 for this statement to be true. So you might think, oh, we can just multiply top and bottom by w minus I and get real and imaginary parts, but it's not that simple, because w is a complex number and has real and imaginary parts within it. So we first need to split w into its real and imaginary parts as well, and then split the whole expression into real and imaginary parts, then equate the imaginary parts and set whatever the imaginary part is on this side equal to 0 to rearrange to give an equation involving u and v rather than w. So you can see it's quite a lengthy process. So let's get started. U plus vi plus 2 over u plus vi plus I. Collect the real and imaginary parts to make it a little bit easier. Now to split this fraction into real and imaginary parts, I need to multiply top and bottom by u minus I v plus 1. And as we usually have, that gives us the real part squared plus the imaginary part squared and no other terms in the denominator. But in the numerator, we have quite a complicated expression. We need to multiply these together. There we go. Now we don't need all of this expression, because the information we've been given is that y equals 0. So we just need the imaginary part to equate that, and that's this part here divided by this denominator. So because y equals 0, we can say that uv minus v plus 1 u plus 2 divided by u squared plus v plus 1 all squared. The imaginary part here also must equal 0. That's nice because we can multiply everything by this and it just disappears. So uv minus uv minus u minus 2v minus 2 equals 0. These two cancel out, which gives us a surprisingly nice relationship between u and v. Rearranged to give v in terms of u, just like you would give y in terms of x, and we get v is equal to minus a half u minus 1, which looks good because we were told it should be a line in the w plane, and this is a straight line equation. Last thing to do, sketch L on an Argand diagram. Don't forget we're using u and v to sketch L because L is in the w plane. It cuts at minus 1 and has a fairly shallow negative gradient. So here is L. This next example is very similar, so we'll go through it in the same way. The transformation t from the z plane to the w plane is given by this. The transformation t maps the points on the line with the equation this. Here's our relationship between x and y that we will use in place of a locus in the z plane to points on the line L in the w plane. Find an equation of L. So we rearrange to make z the subject. Like this. And again, in this example, we haven't got a locus given to us, and it's not so easy to find one from this. Although, to be fair, you could perhaps work one out, both for this one and for the previous example, because these are straight lines, and you could work out a perpendicular bisector that would match this straight line. But in favour of going through this process, we won't go down that road. So we're looking for x plus yi here, and on this side, converting w into u plus vi, and then rearranging this whole thing into one big complex number so that we can equate the real part with x, the imaginary part with y, and then use the fact that y must equal x. So we're going to have I over u plus vi minus 1 times top and bottom by u minus 1 minus vi, and that will give us on the bottom u minus 1 squared plus v squared, and on the top v for the real part and plus u minus 1i for the imaginary part. So if I were to write this out, v over u minus 1 squared plus v squared for the real part, and then plus u minus 1 over u minus 1 squared plus v squared I for the imaginary part. And again, this must equal x plus yi. So the x equals this, and y equals this, and we know for our locus in the z-plane, y must equal x, so I can make this equal this. And then we've used this to find something connecting u and v. So if I jump into a different colour here, and equate v over u minus 1 squared plus v squared with u minus 1 over u minus 1 squared plus v squared, and this is our x equals y statement with u's and v's. Very nicely, of course, we've got the same denominator, so they both cancel out, and we end up with the very simple statement v equals u minus 1, which is our straight line L in the w plane. Part B is very similar. Show that the image under T of the line with equation this in the z plane is a circle in the w plane. State the center and radius. So we've got the same process here, it's the same transformation, which gets us to this same statement, but now instead of x equals y, we've got x plus y plus 1 equals 0. That means I take this part, this is my expression for x with v's and u's, plus y, the expression for y here, plus 1, and set that all equal to 0, rearrange that, and I should get a circle equation. So this is x plus y, then we need a plus 1 equals 0. Not such a nice expression to use, So I'll multiply everything by this denominator. Expand out that bracket. Collect the terms. And complete the square. And that gives us u minus a half squared plus v plus a half squared equals 1/2. So the centre of our circle is at half minus a half, and the radius is 1 over root 2, or rationalising that, root 2 over 2. Part C. Sketch L and C on the same Argand diagram. Here are the two results. We need to put these onto our Argand diagram. And again, remember our real axis is u and our imaginary axis is v. The straight line comes up with a gradient of 1 and goes through -1 on the imaginary axis. This is L. And then our circle, we should perhaps think a little bit more carefully about this. Centre half minus a half. And that should be on the line. Then the radius is the square root of 1 over 2, which is just a little bit bigger than half, about 0.7, so it will cut both axes as it comes around. And take note as well, if you put 0 and 0 for u and v, we end up with the statement a quarter plus a quarter equals a half, which is true, so it also goes through 0, 0. And by symmetry, we can see it will also go through the point here where the line crosses the v-axis, and also over here where it crosses the u-axis. Here is C. Here we've got one final example that was a past paper exam question to show that it's really important to read these questions carefully. I'll go through it first, and then I'll focus on the thing that makes this one different. So we've got the point P represents a complex number Z on an Argand diagram. We've had that before. P is just the name of the point for Z, where the locus of P as Z varies is a circle C with Cartesian equation this. We've had something like this before as well. We can change this into a locus, or we could use the XY relationship, but if you can put it into a locus form, that will probably be easier. So we have Z minus I, and the modulus of this must equal 2. That is giving you the same information as this. A transformation T from the Z plane to the W plane is given by this. That's fairly standard. We've had things like this in the last two examples. The point Q is mapped by T onto the point R, given that R lies on the real axis. We've seen this before as well. That's like saying y equals 0. Show that Q lies on C. Now by this point I've already made the mistake that makes this question so difficult. The mistake is this statement here. To explain this, I'll quickly sketch on the side. The point Q is mapped by T onto the point R. So here we've got our Z plane, X and Y, and T is mapping this onto our W plane, U and V. We've got circle C with this Cartesian equation in the Z plane, that's here somewhere, and point Q is on here somewhere. That is mapped onto the point R, and R lies on the real axis. This is the key point. It's mapping onto this real axis here, and R is somewhere on this. Now we've been given information about R, and we're asked to show that if this is true, it lies on the real axis, that Q must lie on C. This is different to all the other examples, because usually we start at Q, we follow the mapping, we end up on R, and we've got to prove that this is whatever it is. But in this question, they're giving us information about the W plane and asking us to work backwards and show that Q lies on C in the Z plane. To summarize my mistake, this is not y equals 0, this is v equals 0. So compared with all the other examples, this example is kind of working backwards from the w plane to the z plane. What that means for our method is that we don't rearrange to make z the subject, we rearrange to make w the subject, which is kind of nice because w is already the subject. Then we don't substitute w equals u plus vi into the transformation, we substitute z equals x plus yi. Then we go through the same process, but instead of using information about x and y, we use information about u and v, specifically v, to form an equation in x and y. So all the process is the same, but we're going from w to z instead of z to w. Now we're clear on what we're doing, the rest of the problem is fairly standard. I substitute x plus yi in here for z. Three plus I times z, so that's another x plus yi. And then I need to express this in one complex number, real plus imaginary. To do that, I need to deal with the fraction. To do that, I will simplify this quickly in real and imaginary parts. So we've got x plus y plus 1i over 3 minus y plus xi, and then multiply top and bottom by 3 minus y minus xi. On the left-hand side, I can replace the w with a u plus vi. The key point being we know v must equal 0 if r lies on the real axis. And that will give x 3 minus y plus x y plus 1 plus y plus 1 3 minus y minus x squared I. And all of that is divided by 3 minus y squared plus x squared. Now we've got the real part here and the imaginary part here when you separate this fraction into two pieces, and I know that v must equal 0, so I can peel off this part of the fraction and set that equal to 0. Y plus 1, 3 minus y minus x squared divided by 3 minus y squared. X squared equals 0, which is nice, the denominator can go away. Expand the numerator, we get minus y squared plus 2y plus 3 minus x squared equals 0. Y squared minus 2y minus 3 plus x squared, and then complete the square. Y minus 1 squared minus 1 minus the 3 that's still there plus x squared. Then move the numbers on the other side and we get x squared plus y minus 1 squared equals 4, which shows that this does indeed lie on C. There are quite a lot of examples there, some of them quite involved, so I hope now that is enough for you to have a go at the remaining questions from exercise 4e, the chapter 4 review exercise, and at this point in the textbook you can even do review exercise 1 as well. And maybe I'll see you for first order differential equations in chapter 5.